Let's start our study of hydrodynamics. Start with the concept of the distribution function. To describe the state of the gas statistically, we define the distribution function, f, which is a function of the position, the velocity, and the time, such that f dx dv is the average number of particles contained in a volume element d3x about the position x, and the velocity space element d3v about the velocity v at a time t. Macroscopic properties of the gas can be computed from the distribution function. For instance, you can find the number density as the integral of the distribution function in velocity. Integrating in velocity is going to eliminate the dependence on velocity, and you only have then something that depends on the position and the time. You can identify this number density then with the volume density of the material, where the volume density is the individual mass of a particle times the number density of the particles. And finally, you can define the average velocity, which is the velocity moment of the distribution function, the integral of the velocity times the distribution function, again integrated in space, and normalized by the number density. This normalization by the number density is because the number density is the integral of the distribution function itself. So it's the weighted integral of the velocity by the distribution function. And this, by definition, is the average of the individual velocity v. So these quantities, as I said, are the number density of particles, the mass density of particles, and the average velocity of an element of the gas. Further, we demanded that f is positive and that the function f goes to 0 as the components of the particle velocity tends to infinity, so that a finite number of particles has a finite energy. Particularly, the function is positive, is necessary to guarantee that the number density is always positive. Now, to study microscopic properties of the gas, it is useful to decompose the particle velocity v into the average velocity u plus a random velocity that is relative to the mean flow, w. Let's discuss now Boltzmann equation. Boltzmann equation is the evolution equation for the distribution function. We're seeking an equation that describes the change in the distribution function in time. Consider a group of particles that is located in a phase space volume element, dx naught and dv naught, around a position in phase space x naught v naught. We assume that there is an external force, big F, that is acting on the particles so that they experience an acceleration, which is the force over the mass. And for the moment, we ignore collisions and interactions between the particles. The phase space element will evolve from dx0 dv0 into dx and dv around the new position in phase space x and v, where x and v are given by the initial position and initial velocity times its derivatives in time. Now, because of the Hamiltonian nature of the coordinates x and v, this transformation from x naught v naught to x and v conserves volume in phase space. We saw that in the Hamiltonian dynamics, that's Liouville's theorem. So we can write that d3x d3v is conserved in this transformation. The x3 d3v is equal to the initial values by the product d3x d3v. Now we can define the number of particles that is inside the original phase space element. Remember, we defined the number of particles as the integral in phase space of the distribution function. So the number of particles that is inside this phase space element, the original one, let's call it dn naught. Assuming that the number of particles is conserved, we have that in the new element of phase space, we have dn, and dn is equal to dn naught. We replace now x by x naught plus v naught dt, and v also by v naught plus a dt, and t by t0 plus dt. And together with Liouville theorem, meaning that this product d3x0, d3v0 is equal to d3x d3v, then we have that the distribution function in the two positions in phase space is the same. So we just proved that in the absence of collisions, the phase space density of a group of particles is invariant. So I write it in this form and expanded the material derivative. Now, this is known as the collisionless Boltzmann equation or Vlasov's equation. It's also useful to write this in component form, where the convention here is that repeated indices are a summation in all the coordinate axes. Now notice that this equation can be written in this form, where this big W is x and v in a single vector, a 6D state vector of the system. And nabla 6D is a 6-dimensional divergence. That means the divergence in X and the divergence in V. And this equation has the form of the continuity equation. From that, we understand what the Boltzmann equation is saying. The Boltzmann equation is derived under the condition that no particle can jump in phase space. Particles can only go smoothly, that means continuously, from one place to another. Thus, the Boltzmann equation is simply the continuity equation of the flow of particles in phase space.